Good evening and welcome to MAE 113 Calculus. We're doing a tutorial tonight where I'm answering your questions. Tonight we're going to focus on questions that you're going to ask. You can ask them from the chat window. We can go through topics that we've covered in class, exercises, and you can ask me questions through the chat, or you can also ask exercises from the textbook. First thing that I'd like to also announce is that we have a quiz Thursday. I announced this on Thursday, so we've had some time now. Hopefully you were going over some of the topics that we were going to cover for the Thursday quiz. In particular, we'd covered things like indefinite integrals. We had done definite integral, substitution rule, and partial derivatives. I'm going to try to get Moodle to work, and I will send an email out when I get that working, and so hopefully you'll be able to log in through Moodle, and then you'll be able to do like the quiz online. Hopefully this will serve as a dry run for our final exam that's going to happen. I still don't know if they've released the date yet, but again, it's not this week. It's the following, it's sometime next week. So they haven't, I don't know if they've released it yet. Sorry. Yeah, so we'll do that. The final exam, because it's not invigilated, like we can't see you do this, it's going to be worth 25% of your final mark. It will be about 3 hours, and it'll be split. I'm not sure how much questions yet, but there'll be a multiple choice, and there'll be a full solution that you'll have to write out. We talked about that last time on Thursday. Oh, I really hope my voice holds up. And let's see, hopefully. Oh, no, they don't have that. How long will the quiz be open for? I assume like 30 minutes, or I think what I'll do is everyone is kind of spread all across Canada, and what we'll try to do is okay, so yeah, when the quiz open, I'll say like we'll do it for, it'll be available for 30 minutes. Make sure I'll make a note here. And we'll open that at, let's go 9:30 a.m. That's Eastern Standard Time. Okay, does that work for you? Okay. Ooh. 8. Okay. So we'll go through some of the questions in terms of, I was asked about elasticity. So in particular, that was in section, I believe it was in the applications. So they did it in section 3.4. So the question that we had was just an overview of elasticity of demand. I can see Elasticity was from the first week of February, yes. Yes, and the quiz should be going through Moodle. Okay, so an overview of Elasticity. We have just like the yes, we usually have a function, and this is what we call like the demand function. Usually x is the number of units that can be sold, and this f at p is based on the price. So given a price, this would be the number of units that customers will want. And the elasticity of that goes minus the price times the derivative of the demand function all over the demand function. And again, the elasticity if it is, say, greater than 1, we call that elastic. If it's equal to 1, it's called unit or unitary. And the last one is if it's less than 1, it's called inelastic. Now we went through the derivation of it. I'm not sure if that's what you want me to go through again, but again, we can do simple problems like there's also an example here, example 7. But for instance, they have, so when we have to calculate what the elasticity of the demand is, we have to use this function or this formula. And so let's do an example. They have a demand function, and they say that they give us something along the lines of minus 50p plus, say, 20,000. And this could be anything. This is the demand function that we have. Could be anything. It could be for CDs, or it could be for graphics cards, or it could be for basically a commodity. Okay. So yeah, applying this. So then, again, this is a fairly straightforward question because what we would need to do is just take the derivative of that. So we take the derivative of the demand function. So don't have to worry about this constant here. I'm just have this minus 50p. So I'm just left with minus 50. And so, therefore, it's the elasticity function, or the elasticity of demand, is minus p times the derivative up top. So we have minus 50 divided by, and then the original function itself. So minus 50p plus 20,000. Now we can simplify this a bit. I have a minus and a minus, so that becomes positive. So I get a plus 50p all over minus 50p plus 20,000. And then I can divide everything by 50. So by dividing by 50, I get 50 So I'm left with P over minus P plus, and then 5 goes into 24 times, and I'm left with the I'm left with the 2 zeros. So that's 400. And so there's my, and I guess I could rewrite this like that. 400 minus P. So there's my elasticity formula. And then they could say, calculate equals 1. So that equals unity. So what we can do then is we'll have, just solving that. Hopefully I have, okay, good. I haven't gone off the page. So I have P over 400 minus P equals 1. And then I solve for P. So it should be like calculate P or find P. So I got 400 minus P. And then I have bringing the minus P over to the right-hand side, or sorry, left-hand side, so that I have positive P. So 2P's equals 400. So I have 2P equals 400. Divide by 2, so I'm left with 400 over 2, or P equals 200. So, therefore, P equals 200 equals 1. Okay, and you can also calculate other things too, like for instance, we could figure out what the elasticity of demand when the demand is 100. And if it's 100, then we substitute in 100 over 400 minus 100, which gives me 100 over 300, or 1/3. Since this is less than 1, the elasticity is inelastic. So it's therefore inelastic. So that's kind of like the kind of question that would be asked. It would be like, given the demand, find the elasticity, calculate when P, the price, causes the elasticity to equal 1, and then, probably pick a value and then determine whether it's inelastic or elastic. All good? So I'm ready for another question if you have it or not. Oops. So again, I'm taking your questions. If you have a question, just type it into the chat window. It can be a topic or it could be a specific question from the textbook. But again, it's up to you. The whole point behind this was we lost Friday and we also lost Monday. So again, this was to give you an opportunity to ask questions and some some more additional time for topics that might have been difficult for you, or we can go over it again. I think the other thing too is we also had terms like marginal. So for instance, we had functions like c of x, and this would say the cost of producing x number of units of whatever. And if we took the derivative of that, this was the marginal cost. So again, we can, if you take the derivative of it, whatever the function is becomes the marginal function. And sometimes we had done in other, we had done in the integral section, you can take the marginal cost and with a little bit more information, you can actually work it back to the original function. So you can go from a marginal cost and integrate that to get back to the original cost. So again, revenue functions, you can take derivative of that, that becomes the marginal. And there's a profit function, so forth. Okay, so somebody asked me about curve sketching. Just anything in particular about curve sketching, or? Is there a particular topic or review curve sketching? I mean, it's there's a whole video that we did on curve sketching. I'm not sure about which part you'd like me to do, just a review. Okay, sure. Let's pick something like a function like, I don't know. So curve sketching, the idea behind it is that now that we've had all these tools that we learned how to take, we figured out from our pre-calculus, we can figure out what the domain is. From our limits, we can figure out if this has vertical or horizontal asymptotes. We can, for instance, look at intervals of where it's increasing or decreasing using the first derivative. We can also figure out where there's local minimums and maximums from the first derivative. And those are where we are looking at the critical point. The other thing that we can look at is the concavity, and that relies on the second derivative. And when we see that the concavity is switching from, say, concave up to concave down, those are called points of inflection. And then using that information, we just kind of generate a sketch. From this one, in particular, I know it's it's a cubic function. So it'll have some sort of like, I know it should look something like, I don't know, that's like what x cubed looks like. But yeah, so we can just kind of work our way through it, like what I've just kind of mentioned. We have, for instance, so we can do easily what the domain is. Since this is a polynomial function, you know that it's continuous, so it's got to be continuous on the entire domain. So yeah, it's a polynomial. If it was a rational function, for instance, we had something like this. This is a rational function. It's continuous on the reals except for where the denominator is equal to 0. So for instance, this case, this would be continuous on all the reals except for x equals 2. So if we wrote that out in like interval notation, it would be minus infinity up to 2, union 2, and up to infinity. So it's kind of got a hole. Second part. Does this have any horizontal or vertical asymptotes? No, it doesn't. There's no point where this function it's continuous. We kind of know what it looks like. So no, there's no vertical or horizontal asymptotes. We can again, where is it increasing or decreasing? This requires that we use the first derivative, and we kind of have to test a little bit. So for instance, the first derivative of that would be 3x squared minus 12x plus 9. Okay. And then what we have to do is set that equal to 0. So again, set that equal to 0. After this, would you be able to go over question 7 from test to, and then it says the box. Sure. I'll have to go run and grab that test, but yes, I can do that. Okay. So again, we set this equal to 0. We can factor this out. So I can see a 3 can get factored out. So I'm left with x squared minus 4x plus 3. I think that works. Should. So again, adds to give me plus 3, and minus give me minus 3 minus 1 gives me minus 4. So that means that my critical points, or my critical values, should be at 3 and at x equals 1. So okay. So again, substituting in values into this, I have again, if I pick like 0, so 0 here gives me minus 3, and 0 gives me also a minus 1. So I have minus 3 and minus 1. That gives me a positive value. So that's positive, which means that this is increasing. If I pick something like 2, so I pick a value in between 1 and 3 here, I get 2 minus 3, that's minus 1, so that's negative. And then I have 2 minus 1, that's positive. So minus times a positive gives me a negative, so it's decreasing. And then at 3, well, let's pick 4, so I got 4 minus 3 and 4 minus 1, so those are both positives, so it means that it's increasing. So from minus infinity up to 1, it's increasing. From 1 to 3, it's decreasing, and from 3 to infinity, it's increasing. Okay. Good. That's what I have. And which means that for number 4, I was talking about, say, local mins and maxes. From this point at x equals 1, we know that this is a local max, and here this is a local min. Okay, so the next thing that we need to do is, okay, so I have where it's increasing and decreasing. Now I need to figure out the concavity. So with concavity, that requires me to do the second derivative. So again, if I take the second derivative of that, so it's d squared y by dx squared equals, so I can just use this here, so I'm taking the second derivative, so I got 6x minus 12, and again I find the critical values. Now when I do the critical values of this by setting it equal to 0, the x's in this case give me my points of inflection. So I can factor out that 6 to give me x minus 2. So it means that my critical point that I need to look at, or a possible point of inflection, is at x equals 2. So if I plug in, say, 1 in here, into the derivative here, I get 6 times 1 minus 12, so that still gives me negative. So this would be concave down. And if I pick a value greater than 2, say 3, I get 6 times 3 is 18 minus 12. That's positive. So that means that this is concave up. So this, in fact, so for number 6, this is points of inflection. For this 2 here, that's a point of inflection. Because I'm switching concavity, I'm switching from concave down to concave up. And now that I got most of my information, I can start to plot this now. So let me grab a piece of paper here. So if I kind of plot this, I can start to IZG. Okay, so start marking off some of this. I probably might need this. Okay, so again, I just start taking my information that I've collected and I start to mark this down. I know, for instance, that 1 is kind of an important point. This is a maximum here. And this point occurs here at the point 1. And substituting back into my original equation, so I have 1 cubed minus 6, 1 squared plus 9 times 1 plus 2, that equals 6. So that's 1, 6. So 1, 6. And I know that this is kind of a maximum. So I'll just kind of write a little curve there. And then I have 3 here. So again, I substitute in 3 into the original equation here. So I have 3 cubed minus 6, 3 squared plus 9 times 3 plus 2. So that is 2. Okay, and put this here. It's kind of a min. Okay, and the next thing is I have a concavity, so I have it switching from 2. So I should probably calculate what that point is to. So I plug in 2 into this equation. So 2 cubed, that's 8, minus 6 times 2 squared is 4 times 6 is 24. So 8 times minus 24 plus 9 times 2 is 18 plus 2. So that gives me 4. So I have a point of inflection at 2, 4. So there's a point of inflection. And oh, I think I forgot one other thing in here too. I could easily solve for where this is going to intercept into, I think, to the y. So if I wanted to solve for that, it's 2. Bring that over, so minus 2 equals x. It's 9 x. Factoring that out, I get x squared minus 6x plus 9. And make sure I'm doing that correctly. Oh, this is going to be quite difficult. So yes, no, we wouldn't expect you to do that, but we would be expecting you to say find the substituting this for 0. So if we substitute in that for 0, I get 0 cubed plus minus 6 times 0 plus 9 times 0 is still 0 plus 2. So I have another point of 0, comma 2. So here's my 0, and here's 2. And so that's it. There's all the information that I need. It's increasing from up to 0 to 1, so, and it's got to be concave down. So again, something like that, something like that, and there we go. So there's my function, my original y. So there's y equals x cubed minus 6x squared plus 9x plus 2. And that kind of makes sense because the base function itself is a cubic function, so it's kind of got that, it's increasing, there's a point of inflection, and then it, this one's a little got some more concavity to it. But yeah, this is actually concave down at this point, and then it switches concavity and then goes up. So yeah, we can do number 2, number 7, the box one, but I have to go grab the test. So let me just go run and grab it. is number 3. Okay, so these were my solutions that I had for test number 2. This was in question 7 on the box. Cover that up. Okay, so a box with a square base open at the top is made by cutting out identical squares from the corners of a piece of cardboard that measures 1 meter by 1 meter and folding up the resulting flaps. So again, the idea is you can, if this was square, so there's a square there, and then if I had, let's say, identical squares, let's say roughly there, here, here, here. Yes, finding the x-intercepts is too complicated. Yes, it required us to solve it requires you to solve a cubic function. In this course, it's yes, it's beyond the scope of this course. There is a formula for it, but it's complex. Well, it's just very long. So again, the question here is we have identical squares that are cut out. I think we knew how to solve quadratic formulas since the times from ancient India. And I believe the cubic function was found by 2 Italian mathematicians in the 1500s. I believe it was Tartaglia and Cardano. So we have this, and so here's my kind of square, but I've cut out my x's here. So here I've cut out, this is the length, this is x, and here is x. And so again, all these have x's, and the idea was that we can now fold up these little flaps. You could use tape or whatever, but you flip up the little flaps and now you have a box. It's not a great box on my part, but it's a box nonetheless. So we need to figure out what the formula is for that box. So what I can tell you is that if this was 1 meter, the dimension of this side right here, well, this side right here, what I had cut out, that's an x, and here is an x. So if I had cut that out, I started out with 1 along the entire side, so that was 1 meter. And then I took away 2x. So on this side, on this box right here, this is 2x. So that's 2x. Same thing, because it's all squares, the same thing applies here. So again, there's 1, I subtract. So I had 1 meter and I took away 2x. And I can already tell you what this side here is x. So again, now I can fold this up. I'm going to fold this up the other way. Just because I've written down the sides. So this side here, this side along here is 1 minus 2x. This side is 1 minus 2x. So there's my length and my width. And then what's my height? My height is x. So that is my formula for that. So again, my volume is equal to length times width times height. Now my length or my width, it doesn't matter because they're both the same. So that's 1 minus 2x. And I multiply by the width here, which is 1 minus 2x. And then I have my height is x. So that's how I got kind of the formula. And I've written in this formula out. It's now all based on x. And so what you can actually do here is substitute in 1/10. So the volume at 1/10 is equal to 1 minus 2 times 1/10 multiplied by 1 minus 2 times 1/10 multiplied by 1/10. So I'm left with 1 minus 2 over 10 multiplied by 1 minus 2 over 10 multiplied by 1/10. So that's equal to 10 over 10 minus 2 over 10, so that's 8 over 10 times 8 over 10 times 1 over 10. 8 times 8 is 64. 10 times 10 times 10 is 1,000. And that's also equal to 0.064 meters cubed. Now we found our formula here. So you could have left it like B, just like this formula right here. You could expand it out. And that makes it a little bit easier when we start to take the derivative of that. But it's not asking for this at this point. So I have my formula here, and the next part here is each side of the box must be non-negative. What inequalities must x satisfy, and what is the domain of v of x? Okay, well, each side, so the height has to be non-negative, which means that it's got to be greater than or equal to 0. And also this side here, or this side, it doesn't matter because it's the same. 1 minus 2x also has to be greater than or equal to 0. And we solve for this, which means that bringing this 1 over to the right-hand side makes it minus 1. So I have minus 2x. When I divide by minus 1, the sign flips. So I have x is less than or equal to 1/2. So combining these two together, it means that x has to be greater than or equal to 0, or 0 greater than or equal to x, which is greater than or equal to 1/2. Sorry, yes. So x has to be less than 1/2. So what I'm trying to say is this is the domain. I have x is an element in the interval, the closed interval, because I have these inequalities. This is less than or equal to 0, 1/2, and this is the closed. Why is it important that it's closed? Because the next part is we have to find the volume x that maximizes the volume of the box. And remember, when we were maximizing something, to find, say, a maximum, here's a maximum here, we need to have a closed interval. So again, I could have a closed interval, and here's also a max. But I need to make sure that I work on a specific closed interval. It makes me focus, and I have to check the endpoints. So to find the maximum, I need to, it means that if I'm doing the derivative, let's use a small piece of card. So it means that right here, I need to make sure if I drew tangent, as I'm going up, 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 I'm looking for spots where the derivative is equal to 0. And when the derivative equals to 0, this is a possibility that it could be a maximum. So to do that, I need my v of x. And we've already calculated what that was. I have it here. I'll just rewrite it. Okay, so there's two ways I could do it. I could expand this out, or I could take the derivative. I can simplify this because I have this times this, so that becomes 1 minus 2x all squared times x. And from that, I can actually do the derivative of that. So using, I have a product and a chain rule that I have to apply. So I have to do the product rule. So I have to take the derivative of the first function times the second function unchanged plus the first function unchanged times the derivative of the second function. Now when I take the derivative of this, I have to, do chain rule. So the 2 comes down, I leave the inside alone. This drops by 1, and then I have to take the derivative of the inside, and in this case it's just minus 2. I don't forget about that x here, so there's the x plus 1 minus 2x, and then the derivative of x is just 1. So I have minus 4x times 1 minus 2x, and then I have plus 1 minus 2x. Now remember, I have to be able to solve this. So I could factor this, I have to set this eventually equal to 0. So I'm going to factor out this 1 minus 2x. So factoring out that 1 minus 2x leaves me with minus 4x plus 1. Done. And now I set that derivative equal to 0 because I want to find where the tangent is equal to 0. And I set that equal to 0. So that means that it's 1 minus 2x equals 0, or that's equal to minus 1. So minus 2x equals minus 1. And dividing by both sides by minus 2 gives me 1/2. And the other one that I need to look at is minus 4x plus 1 equals 0. Minus 1 minus 4x. X equals 1/4. So those are my two values that I'm interested in. The other thing too is we also know that this is within the domain, so that's good. Lastly, so I'm working, these are my points I need to look at. I'm working on the domain 0 to 1/2. So what I need to do is calculate what the volume is at 0, at 1/4, and 1/2. So remember, this needs to go back into the original equation. So these are my critical values. That's where it's likely to be the max. But if I already know that these are 0 if I do the derivative, make sure that you're plugging these values back into the original function. So if I plug in 0 into the original function, 0 times whatever still gives me 0. If I did, let's do 1/2. So this is, oh, did I do something wrong? Oh, it's quite possible that I made a mistake. Just a second. On the test solutions, you had 1/6 instead of 1/2, 1/4. Yes, I did. I screwed up, and I know where I did it. I didn't factor out something properly. I dropped a 2 here. No, I didn't. Oh, I did. I made a mistake right here. I missed the 2 right here. See, there's the 2 that should have been here, and I didn't copy that down. And so here's the squared there. So again, this would be incorrect then. Sorry about that. Yep. So I can factor out that 1 minus 2x. And so I'm left with minus 4x plus, and now I factored out one of these, so I'm left with 1 minus 2x still here. So I have 1 minus 2x. I have minus 4 minus 2, so that makes it minus 6, and then plus 1. Miracle of paper. I can cover that up, pretend that never happened, and carry on. Setting this equal to 0, I get 0 equals 1 minus 2x, or x equals 1/2. And over here I have minus 6x plus 1 equals 0. So Aiden did that. Does that help now? Yes, I dropped a 2. I didn't copy it into the next line. I dropped a squared. Okay, perfect. Which then means that I have my 3 values I need to look at: 0, 1, 6, and 1/2. Okay, so again, 0, substituting it into here, 0 multiplied by everything, so that's still 0. Let's do the 1/2. So I have 1 minus 2 times 1/2 squared times 1/2. So that equals, this cancels, so I got 1 minus 1. So that's 0 squared times 1/2. So again, that's equal to 0. Did I do that right? Yes, good. And lastly, I have 1 minus 2 times 1/6 squared times 1/6. So I'm left with 2/6. So, or 1/3. So that makes it 2/3 times 1/6. Make sure. I'll write it out. 1 minus 2/6 squared times 1/6. And then I'm left with 6 minus 2 gives me 4. 6 times 1/6. Hopefully I'm doing this right. Nope. Because again, this has to be squared. So it's 16 over 36 times 1/6, which leaves me with 16 over 36 times 6. If it's like, it's 3 dice, which gives me to 16. Oops, and I'm writing it off the sheet. Sorry. Okay, so there it is. That's the maximum. So just finishing it off, and then it says state the dimensions of the box with the maximal volume. Don't forget. Okay, so again, to do that, to get the dimensions, is I'm just substituting in. I found that it was 1/6. Am I on the right? Okay, good. I am on the page. I found that it was the 1/6. So my Vx is equal to, I have x times 1 minus 2x times 1 minus 2x. So the maximum was 1/6. I have 1 minus 2x, so that's 1 minus, again, 2 over 6. 1 minus 2 over 6. So that equals 1/6 times 4 over 6. 4 over 6. So you could actually reduce that down, and that's what I did. So it would, the dimensions would be 1/6 meters by, so you could write 4 over 6 or 2/3 meters by 2/3. Good. Again, that was the second way that I saw people doing it. My instinct was basically to just expand everything out. So I would have just taken what I had for my volume and expanded it out, so that I had that, in the end I got Vx is equal to x minus 4x squared plus 4 times x cubed. And then I could have taken the derivative easily of that. That's just, it's a derivative of a polynomial. So there I get 1 minus, I get 8x plus 12x squared, and then I just factored it. So same idea, I believe. It would just work out to 4x minus 1. And factoring that is 6x minus 1 as well. And set that equal to 0. And you'd still get the same answer, which is 1/4. And also x equals 1/6. Okay. I probably won't scan those sheets again because the solutions are written much nicer here. But again, there's two solutions. Like again, there's lots of different ways to do something. You could have, that's why I have two solutions. I saw it pop up, and so just look at the solution that you wrote down. And again, those numbers along the side was what I was assigning marks for. So like again, like 1 mark for doing A, 2 marks for doing B, 1 mark for doing C, 5 marks for doing D. So again, where are those 5 marks coming from? Knowing that you have to take the derivative, knowing that you need to set it to 0. There's 2 marks there. Then solving, so there's 3, 4, and then maybe 5, making sure that you calculate this. You have to also state that its maximal volume is 16 over 216. And then again, 1 mark for just recognizing, again, people want to know what the final answer is. Like you want to know what the actual box is going to look like. So sometimes we've done all this work and you have to give a final answer. People don't seem to enjoy the math. They won't read through it. They just want to know what the final answer is. So again, if you're working for somebody, you do all this beautiful math, and then they go, okay, well, what was the answer? Again, sometimes we have to state it. Again, there's a curve sketching question, but there's other problems like that in the textbook, I would say. Also, if you're looking for other questions for curve sketching, other questions in the textbook, for instance. Here's the textbook. There's questions like this where, again, you're using the information summarized in the table and sketch that. Or we'll probably prompt you and say, like, here's a function and fill in that table. Or, again, probably don't memorize all these guides to curve sketching. But again, it kind of comes down to, there's kind of like 3 elements to this right here. And I'm going to say, the first 2 here is kind of like your pre-calculus. This is kind of like what the functions are doing in terms of what the domains are and the intercepts of the function. 3 here is kind of where we start to use our limits. So there's kind of limits. So that's as looking at the limits or the behavior as it's going to infinity. Finding the horizontal and vertical asymptotes. This part right here breaks down to the first derivative. Again, finding where it's increasing and decreasing. Finding the relative maximum and minimums. Again, that's all to do with the first derivative. Then there's the points, there's the second derivative. And when we take the second derivative, we can look for the concavity. We know where the points of inflection are, and then plot. So that's kind of how these 9 steps break down to the pre-calculus stuff, the domains, the intercepts. The second ones are the limits, what's happening out at infinity. Then we can use our first derivatives to find increasing and decreasing, where the maximum and minimums are. Because again, if it's increasing and decreasing, we know that we have increasing, decreasing. Well, at this point, this has to be max. And if it's decreasing and then increasing, we have a minimum. And then we have our second derivative stuff, which is the concavity. I'm trying to not write in the textbook. That would be terrible if someone else got this book and it just has all my scribbling in it. So in here, this is telling you what's happening at the infinities. This is telling you what's increasing, decreasing, and you should then be able to figure out from this where there's a max and where there's a min. And also from here you can see where a point of inflection is by looking at what the concavity is, because it's switching from one to another. And that's what I have done. On the grid, I just start to kind of go, okay, from here, from minus infinity to infinity, or to -3, this is decreasing, so I know it has to go down. I know from here to here, this has to be increasing and decreasing. So I just, as I'm reading through this, I just start to write down what I'm given. Again, this is a problem-solving approach. This is all the stuff that I know, and then I kind of know what the shapes of concavity being up and concave being down, and you just start to slowly sketch it out. Once you have enough information, you kind of figure out what to do. You know, this is a plausible curve that fits this criteria. This is not necessarily the solution. Again, it could, you know, come up really up higher and then come back down, but again, the general shape of it should look, you know, fairly similar. If you're going through tests like this, yes, so very quickly you should know what these shapes look like. E to the x looks like that. Ln x is the inverse of that, and again it crosses at 1, 0. X, it's just a straight line, and minus x squared is a quadratic, and it's concave down. And you just look at the graph in A, because it says what's the limit as x, e to the x goes to minus infinity. Well, go out to here. It doesn't touch 0. It gets close to it, but it doesn't touch it, and that's the limit. Then as we go to positive infinity, this screams off to infinity as well, so that's B. In terms of looking at this function, it's definitely not increasing. This is decreasing. This is what we would like to see in terms of our pandemic. We would like to see our cases decreasing. So this is increasing. Increasing would be going up, and this is going down. So that's not increasing. This is not concave down. Concave down would look something like this. So it's definitely not. This is concave up. This is helpful. Again, you don't really need to use a calculator for this. This is just using your rules. So, you know, all I've done here is I've rewritten it here. I can pull that 2 up to the top here, so I get 2 squared. And then I can simplify this because I'm adding these two ones together, which is just multiplying these terms on the inside here. So it's just log of 3 of 2 times 2 squared, and that simplifies to 8. So it's log 8 of base 3. So it's just A. Again, very straightforward, just switching it back to the exponential form. And I just know that 3 to the 4th is 81, so therefore x equals 3. Again, this is testing to make sure that you know that this crosses at 1, 0. And it doesn't matter what base I pick. This could be log 1 of base 4 or log 1 of base 10,000 or whatever, it's always going to be 0. So, and again, just exchanging, just writing out using your exponential forms. And again, using this rule here, I have an exponent. I can bring that in front. So that drops down in front here. And I'm left with ln e. And ln e is equal to log e to the e. And that always equals 1. So again, that was another rule that we have too. Any base, so log b to the b equals 1. For number 2, there's critical numbers, stating where the critical numbers are. Just looking for where the derivative is equal to 0 or it doesn't exist. Those are our two cases. And in this case here, the derivative is equal to 0 is where it's, let me use this. It's right here. That's where the tangent is flat. So it's at 2. And the derivative doesn't exist here because if I try to, it doesn't exist because it's not continuous there at that point either. So it does not exist. Number 3, again, because these things can be easily looked up in terms of this kind of question in your notes, you don't have to really worry about proofs like this. Because, well, this could be easily looked up or done on a calculator or whatever. So something like this probably won't show up on an exam. Again, because we can't really monitor everyone. So, but the proof, again, using, I saw some people did really well on this. Some people didn't do so well on it. Some people didn't write it at all. But I gave you the definition of the derivative, and there it is up top. So again, I just rewrite it. I substitute in my f at x plus delta x. So in this case, I'm using my e to the x. And using my exponential rules, I can rewrite e to the x plus delta x is equal to e to the x times e to the delta x. I can factor out that e to the x here, so I'm left with e to the delta x minus 1. And I can bring this out in front because this e to the x does not depend on this delta x out front here. So I can bring that out, and that's basically, I treat it like a constant because, again, I'm not varying it. So the e to the x comes out front, and I'm left with the limit as delta x approaches 0 of e to the delta x minus 1 over delta x. And by the hint up here, that's equal to 1. So by the hint here, I just have now e to the x. So that proves that the derivative of e to the x is equal to e to the x. Which is great, because it's also nice because when we did our integration, we're always looking for the antiderivative, so we're kind of thinking about going backwards. But in this case, it's e to the x. Remember, when we're doing the integration, though, we lose a little bit of information. We need a plus c, or a constant of integration. So here was the standard, the demand equation. Again, here we have f of p, so there's kind of our demand function. I wrote f of p because, again, people would get confused if I just wrote x equals and then 10 square root of 50 minus p over p. Like, they're just like, that's not equal to x. Okay, anyways. So I wrote f of p. So hopefully if you recalled your formula for the elasticity, it's equal to minus p times the derivative of the demand function over the original demand function. So again, here I needed to calculate the derivative. So there's me calculating the derivative, and then I put it into here. So I have minus p, and there's the derivative, and then I also need the I need the original function here in the denominator. So I just kind of spread that out over a longer fraction. Simplify it. And again, very similar questions. You get something nice. You got 25 over 50 minus p. You're asked to solve for when this equals 1. So again, the elasticity, the price equals equals 1. Solve for p, and you find that it's p equals 25, so $25. And this was straightforward enough that if you plugged in 26 into the original equation, you got 25 over 50 minus 26. That's 25 over 24. That is definitely bigger than 1. You don't have to calculate that. You don't, just 25 over 24 is good enough, and you know it's greater than 1, and so therefore the demand is elastic. Number 6, don't be too scared. I know there was a lot of room on this for there's 3 marks. So it was because I wanted to keep question 7 and 8 all on the same page. So question 6 got a lot of room. So there's 2 solutions for that. There's a kind of what I would have done, which is just straightforward, is looking for a quotient rule application. So again, applying the quotient rule, derivative of the top function times the derivative, or the bottom function, minus the top function times the derivative of the bottom function, and then multiplied by the bottom function all squared. That's it. That's all I wanted to see. There's a little bit of a trick, like a little bit of when you're taking the derivative here, because it requires you to use chain rule, because I have something in the exponential here. So I needed to do chain rule here. And again, I say right down here, taking the derivative that requires a chain rule. So again, it's the derivative of the outside function. In this case, it's the exponential function. But the derivative of the exponential function is itself the exponential function, so I don't touch it. So I just write it again. And then I take the derivative of the inside function, which in this case is the exponential here, and the exponent. And I have to just take the derivative, which is just 2x minus 4. So there it is. And that's it. And so that's all that I needed to see, was basically, even if you didn't write out this step, just even that was good enough for me. There again was a quicker way you could simplify this, and then when you did that, it was very easy as well to take the derivative of that. And again, this is fully simplified, which was kind of cool. This is a fairly straightforward question. You have a function. This is the position function. The first derivative is the velocity. The second derivative is the acceleration. What became a little twist on the question was knowing that I said the maximum velocity. So you needed to look at this. I'm asking where the maximum is of this. So I wanted this, the maximum of this equation, which means that you take the derivative and set equal to 0. And by doing that, you just look at here. So I just needed you to look at this and set that equal to 0. So you find that that equals 0 when t equals 1. I tell you the maximum on the interval 0 to 5. So again, it's a closed interval. So 0, 5, and 1. And you calculate those values, and you look basically for the biggest number. And in this case, it's 13 meters per second. That occurs at time equals 1. So good. And then what is the acceleration of the car when t equals 2 seconds? So again, just substitute in 2 into your second derivative, which you've already calculated here. So 6 minus 12 gives you minus 6 meters per second squared. And we did 7 and 8. So that was kind of test 2. Yeah, in general, it was good. What took the longest was trying to scan all of it on my home scanner. That's what took the longest, and then emailing it individually and just through that webmail applications took a while. So I appreciate everyone for I wish I could have handed it out in class, but pandemic, once in a lifetime, once in a century event. So okay, so is there any other questions that we have? I hope so too. Yes, we hope that's a once in a century event. Can we do a bit more integration if we have a few minutes? Yes. Yes, we can. Any particular questions that you have, or I can just pick random ones out of the book, and hopefully I don't drop any squared or whatever. Okay, let's do a simple one, or a straightforward one. So let's evaluate this. I have the indefinite integral, so I don't have to worry about calculating a final number. But I'm going to be integrating ln x all squared over 2x. We don't really have a rule to do that, so we kind of know that we'll have to use substitution. So the more You said 75% of the term work under the exam. Could you explain that? Yes. So 75% of the term work, so that would be all the work that we've done, like quizzes, tests, would now count for 75% of the mark. I'd have to scale that, and so that would count 75% of your mark, and then 25% of that would be your, and then 25% is the exam that we're doing online. Does that help explain the marking system? I'll probably write out exactly what that scales up to, but again, because the exam isn't proctored. Is that okay, Aiden? Does that explain? Okay, perfect. Yes. So basically, I'll just scale it. I'll probably write out the actual like final totals, percentages of each, the quizzes and the tests. But those are important because, again, those are things that we saw you write. Those are things that we invigilated. And so I'm perfectly fine at 25% to have a non-invigilated exam. So, and I think, yeah. Okay. So if I let u equals ln x, and then I take the derivative of that, the derivative of ln x is 1 over x. I can't forget about the differential. There's dx. Okay. So, I have ln x squared. Then I also have 1 over 2x dx. I can't replace the 1 over 2x dx yet with du. Not yet. But what I can do is I can bring that 1/2 in front. It's a constant, so I can bring it out in front. So I have 1/2. And then the integral of ln x squared times 1 over x dx. And that means that I can replace this now with du, and this is replaced with u squared. So now that is equal to 1/2 the integral of u squared du. And this is straightforward enough. We use our integration power rule, so this goes up by a degree, and we also put that 3 in the denominator, plus a constant. So I have 1/6 u cubed plus 3, and I'm almost done. I just need to replace that, that u with what I had said that u was going to be, which was ln x. So that's ln x cubed plus c. And I mean, I can do one more. Okay, let's do this. So again, this is to evaluate this integral. Oh, good. I'm within the window. That's good. I mean the window, like for the camera. This looks to be the more complicated part right down here. So I'll let u equal that, which is the 3x squared plus 1. And then taking the derivative of that, I get 6x dx. So I've got this part down okay. I got the 1 over u part here. But I need to replace this x dx here. So, but I don't have a direct replacement. I have 6x dx. So again, I can just bring this over to the other side here. So I got 1/6 du equals x dx. And now I can replace that. So x dx is equivalent to 1/6 du. So integrating that, it's 1 over u times 1/6 du. And I can pull that 1/6 out in front. And the integral of 1 over u is our special rule. That's the ln x. So ln of x plus a constant. Oops, should be u here. And at this point, I'm going to replace the u with my function that I had substituted it with. So and that's it. If you want it to be a little neat, since is always greater than 0, you don't really need to have the absolute value. So some people could drop those at this point here, and that's your final answer. And that's integration by substitution. Just, again, reducing back to a problem that we already know how to solve. I can break it down to 1 over u, 1/6 du. That 1/6 comes out in front. Now I just have to integrate 1 over u, and using our rule, that's ln x, or ln u in this case. And that's it. So I think that's as much as I can do tonight with my voice. I'm trying to not cough into the microphone. So I'm going to have to call it quits for tonight. I'm sorry. But if you have any more questions, again, you know where you can reach me. Again, email. I'm only just a couple taps away. So just send me an email. I'll send you a response back quickly by, I usually have my phone nearby. And if it's a little longer than, if it's a question about the textbook, I can't dictate a solution into my iPhone yet. I wish, but I'll try to respond within an hour or two with a written thing. Okay, so I hope this helps you. I hope that this gives you a little bit more confidence going into Thursday, and the Thursday is designed so that we can have a bit of a dry run on with the Moodle system. Again, I have to look into the Moodle and get it running, and I will send out an email as well to tell everyone, and you should be able to see it pop up in your, I guess, whatever kind of the main page of Moodle, and you should see our course pop up eventually. Okay? I hope you guys all have a good night. Stay safe. social distance and enjoy doing some kind of integration. Okay, take care.